Hello everyone. In this video, we will discuss about the semiconductor diode. You will learn about the charge carriers of semiconductor, the doping of semiconductor, the P-N junction, forward bias and reverse bias, diode as rectifier, and the capacitor smoothing. What is conductor? Conductor is material which allow the current flows easily because they have so many free electrons. For example, the gold, silver, aluminium, and iron. And then the insulator is the material which do not conduct the electric current because they have too few free electrons to move between the atoms. For example, the plastic, the glass, the polystyrene, and oil. The most important thing for the material to conduct electricity is the free electron. Because the free electron is the one who carry the energy. And then what is the semiconductor? Semiconductor is material which has the conductivity between the conductor and insulator. For example, the silicon, germanium, boron, tellurium, and selenium are some examples of the pure semiconductor. So the semiconductor characteristic is between the conductor and insulator. So we look at the silicon and the germanium structure. So a silicon or germanium atom has 4 valence electrons in the outermost shell. So as what you can see in the diagram below, this is the silicon and this one is the germanium atoms. So this is what we call the electron valence. So for the silicon and germanium, we have 4 valence electrons. So for the germanium also 4 valence electrons. So the electron in the outermost shell all are involved in perfect covalent bonds. So leaving no free electron to conduct electricity. So in this case, it is an insulator. So this is the covalent bond. Four electron valence form a perfect covalent bond. Then no free electron to carry the energy. So in this case, it is insulator. The characteristic of semiconductor is insulator. So we have two types of charge carrier in semiconductor. One is electron, another one is holes. At very low temperature, pure silicon crystal is nearly an insulator. However, when the temperature is increasing, the thermal energy of the vibrating atoms causes some electron to break free. When the electron break free, it leaves a vacancy. So the vacancy is called a hole. Later on, we will discuss the meaning of electron and hole as a charge carrier. So semiconductor is an insulator when the temperature is low, and it is a conductor when the temperature is increasing. That's why the characteristic is between the insulator and conductor. So this diagram shows the forming of holes from the covalent bond. So when electron is leaving from the covalent bond, it leaves an empty space. So this empty space is where the electron leaving. So normally we assume this hole is a positive. So electrons are the negative charge carrier, and then the holes are the positive charge carrier. And this animation shows how the hole is moving and the electron is moving. So the orange arrow shows the electron is moving, fill in the hole, and then leave an empty space. So this empty space will fill by the nearby electron. So now electron is moving, and then the hole also look like moving. So the direction of the electron flows are always opposite with the direction of the hole is flowing. So actually the hole is not moving, only the electron is moving, but look like the hole also moving. So for a semiconductor, as long as electron is moving, then energy can be carried from one point to another point. So when energy is moving, that means current is flowing. So if the voltage is applied, then both the electron and the hole can contribute to a small current flow. To produce conduction of electron, temperature or light is used to excite the valence electron out of their bond. Then we look at the meaning of doping of semiconductor. The conductivity of semiconductor can be increased by adding a small amount of certain other substances, or we call impurity. The process of adding the certain amount of impurity to a semiconductor is called doping. Atoms of impurity should have almost the same size as the atom of the semiconductor. So the purpose of adding impurity is to increase the conductivity. The conductivity can be increased. And then the process of adding is called doping. Then we look at how we add in the impurity will increase the conductivity of a semiconductor. So we have two types of doping. One is N-type doping. So we see what is N-type doping. N-type doping is when we add in the impurity. So impurity here is the other substances which has almost the same size of the silicon. And this impurity atom will have 5 valence electrons to produce the N-type semiconductor by contributing extra electrons. So as what shows in the diagram, 4 of the electron forms the covalent bond. So the impurity we add in here is the antimony. So here is the free electron, extra electron. So this extra electron can easily move from one point to another point to carry the energy. That's why the conductivity is increasing. Conductivity is better than the pure semiconductor. So the pentavalent atoms are called donor atoms. For example, the arsenic, phosphorus, and antimony. The free electrons are the majority charge carrier and the holes are the minority charge carrier. And this diagram shows the energy level. So if you want to get an electron out from the covalent bond, it needs more energy compared with a free electron to conduct the electricity. So this is the energy level for the extra electron, because extra electron is at the outermost shell. So it is easier to excite the electron to conduct the electricity compared with you want to get an electron out from the covalent bond. So this is the comparison between the energy level. So that's why N-type semiconductor can conduct the electric easier compared with the pure semiconductor. Then we look at the P-type doping. So what is the difference between N-type and P-type doping? So for P-type doping, we add in the impurity atom with 3 valence electrons. So this will produce a P-type semiconductor by producing a hole. So for example, we use boron, and this impurity has 3 valence electrons to form the covalent bond 1, 2, and 3. So this is the empty space, then we call holes. So these holes will allow the electron from the nearby to fill in. So this one we call the trivalent atoms. So trivalent atoms are called the acceptor atoms because accept the electron in. For example, boron, aluminium, and gallium. So the hole now is the majority charge carrier. Then the extra electron are the minority charge carrier. And this diagram also shows the different energy level. So if you want to get an electron jump to another hole in the covalent bond, it needs less energy compared with an electron out from the covalent bond become a free electron to conduct electricity. So in this case, the P-type semiconductor also can conduct electric easier compared with the pure type semiconductor. That's why the doping process will increase the conductivity, either P-type doping or N-type doping. So this is the diagram shows the hole and the electron which conduct the electricity in the semiconductor. So you can see here I label the number 1, 2, and 3. So 1 here is the free electron moving. And then number 2 is the electron jumping from one hole to another hole. Then number 3 is the free electron from the covalent bond. Next, we look at the diode. So these are some examples of the diode. So a semiconductor diode is also called a P-N junction diode. So why we call the P-N junction diode? Because it consists of P-type semiconductor and N-type semiconductor which fuse together. That means we have two layers of semiconductor. One is P-type, another one is the N-type. So the region of P-type, N-type, we call the anode and cathode. In a P-N diode, current can flow from P-type side to the N-type side. That means current flow from the anode to the cathode, but cannot flow in the opposite direction. And this is the structure of a diode. Anode consists of P-type semiconductor. Cathode consists of N-type semiconductor. And this is the symbol of a semiconductor, a symbol of a diode. Then we look at the P-N junction. A P-type material mix an N-type material across a bounding region we call the depletion layer. At this region, some free electrons from N-type diffuse across the junction into the P-type and fill up the holes. The holes from P-type appear to move across the junction to the N-type. As a result, the P-type becomes more negative and the N-type becomes more positive. So this diagram shows the P-type and then the N-type diffuse together. So N-type consists of a lot of free electrons, where the P-types of semiconductor consists a lot of the hole. So when diffused together, the electron will attract to fill in the holes. So for this atom, when electron is moving, fill in the hole. So this atom will lack of one free electron. Then this will become an ion positive. And this atom, when receive the electron, it will become negative ion. So this process will repeat, where more free electrons from the N-type semiconductor will fill in the hole in the P-type semiconductor. So the ion positive and negative will getting increasing. So this one is what we call the depletion layer. So the moving of the free electron will stop because it will repel by the negative ion. So that means the movement will stop until a certain thickness of the depletion layer. So this diagram shows the electron being repelled by the negative ion in the P-type semiconductor. So this is what we call the junction potential, because one side with higher potential, another side with the lower potential. So this will result in a potential difference across the junction, which is called the junction voltage. So the effect of junction voltage is to prevent the charges carrier across the junction. In order for electric current to flow, the voltage applied across the diode must exceed the junction voltage. So the junction voltage for the germanium is 0.3 volt, and then the silicon is 0.7 volt. So that means your voltage supply must greater than this 0.3 if you are using the germanium semiconductor, and then your potential difference must be exceed this 0.7 volt to allow the current flow for the silicon semiconductor. So the graph is showing the value of the junction voltage. So this is the germanium diode. That means you are using the germanium semiconductor, and this one is the silicon semiconductor. So for the germanium, the junction voltage is 0.3. That means your voltage must be supplied more than 0.3 to allow the current flow. And then for the silicon, the value must be greater than 0.7. Then you have the current flowing. Because when the potential difference exceeds this 0.3 and 0.7, the electron get enough energy to pass through the depletion layer. So we look at the difference between the forward bias and the reverse bias. So forward biasing the P-N junction will drive the holes to the junction from the P-type and move the electron to the junction from the N-type material. At the junction, the electron and holes combine so that a continuous current can be maintained. So this is the connection for the forward bias, where the positive must connected to the P-type, and then the negative must connected to the N-type of the diode. So this is the symbol that we use in the circuit, electric circuit, and then the light, the bulb will light up when it is a forward bias. So the flow of the current is follow this arrow. So you look at the symbol of the diode, it look like an arrow to show the direction of the current. So this is the forward bias. And this diagram shows the connection of forward bias. So this is the terminal positive, this is the terminal negative. So the battery voltage must be greater than the junction voltage. For example, the silicon. So if the silicon junction voltage is 0.7 volt, then your battery must be greater than 0.7 volt so that the electron can pass through this depletion layer. So that's why the forward bias allows the currents flowing. And then we look at the reverse bias. So the reverse bias of P-N junction, the negative terminal would tend to inject the electron into the P-type material, causing the further depletion of the holes. So the positive terminal would pull the electron from the N-type material. So this will produce a widening of the depletion layer. So you can see from this diagram, so the connection is reverse. positive you connect to the cathode, negative connect to the anode. So the bulb does not light up. So we look at the diagram here. So this one is positive, this one is negative. So the electron from the cathode will pull towards the positive terminal, and the hole also will move towards the negative terminal. So as a result, the depletion layer is increasing. The depletion layer is increasing. So when the depletion layer increasing, the junction voltage is increasing. The junction voltage is increasing from 0.7, maybe increase to 0.8, 0.9. It depends on your battery. If your battery is 1.5 volt, the junction voltage will increase until same with the voltage of the battery, which is 1.5 volt. So when the junction voltage is increasing, that means the ion positive and negative is increasing. So ion positive, negative increasing, then the electron is getting more difficult to pass through, because it will repelled by the negative ion in the P-type semiconductor. So in this case, no electron can pass through this depletion layer, because getting wider and wider, the voltage getting bigger and bigger. So that's why for the reverse bias, electron cannot pass through. So as a result, diodes only allow the current flows in one direction, which is forward bias. So there is the difference between the forward bias and the reverse bias. So now we look at the diode as rectifier. So what is a rectifier? A rectifier is electrical device that convert the AC current to DC current. So that is through the process of the forward bias and the reverse bias just now. So this process we call the rectification. So sometimes the question will ask, what is the meaning by rectification? So rectification, you must write it is a process. It is a process where you convert the alternating current to direct current. So the device is rectifier, and then the process is rectification. So we have two ways to convert the alternating current into direct current. One is the half wave rectification, another one is the full wave rectification. So we look at the difference between these two processes of rectification. So this diagram shows the connection of the diode for a half wave rectification. So for half wave rectification, we only need one diode. So on the left is the AC current. So this one is the input. This is the input AC current. And then the output will be DC. The output will be DC. So before that, we look at the AC current. So AC current is flowing in two directions. We look at the first half of the cycle. So when the current flow in this direction, the direction is forward bias. This one is the forward bias of the diode. So the current can pass through. That's why the resistor will receive the current. And then for the second half, the current is reverse bias. Alright, so the second half is the reverse bias. That's why no current can pass through. So the value will be 0. So that is the half wave rectification, which allows half of the cycle of AC current pass through. So the output will be a direct current. And then this is the graph of the DC current produced. So this diagram shows the full wave rectification. So for a full wave rectification, we need 4 diodes. So these 4 diodes we call the bridge rectifier. So the direction of these 4 diodes must be correct to allow the current flows. First of all, we look at the half wave of the alternating current first. So we see how the current is moving. So this arrow shows when the current flow in this direction. So it will pass through this diode. So we maybe can label this D1, D2, D3, D4. Alright, D1, D2, D3, D4. So the current will flow through this D2 because this is the forward bias. It will not flow through D1 because it is reverse bias. So this one is the forward bias. So the current will flow through D2 and then go to the resistor. So remember, this one is the output. And then when go back, it will flow through D3. And then go back. So this is the first half. Then we look at the second half. So second half is flow in the opposite direction. So we look at the blue color arrow. So when current flow in this direction, it will flow through D4 because forward bias, and then also go through the resistor in the same direction. So as you can see here, they are same direction. So you look at these 2 arrows direction. For the orange color one, the direction is same with the blue color one. So that means the current flowing here is a direct current, even though you are using alternating current. But because of this bridge rectifier, the current flow through this resistor are the same, even though the current reverses the direction. So after pass through this resistor, then go back, follow this D3. So this is how the current flow in a bridge rectifier. And then this is the graph produced for the DC current. So this is what we call the full wave rectification. That means the first half cycle, second half cycle, current can pass through. So these are the diagram of some bridge rectifier, which has four terminals. Then finally, we look at the capacitor smoothing. So the output from the rectifier circuit can be smoothed by connecting a capacitor across the resistor. So this is the half-wave rectification just now, where we use one diode for the half-wave rectification. So if we want to smooth the current produced, we add in a capacitor. So capacitor connection must be connected parallel with the resistor. And then this one is the full wave rectification. So the capacitor also connected parallel with the resistor. And these are some different types of capacitor with different capacitance. We have a smaller size of the capacitor, and also we have a big size of capacitor. Then we look at how the capacitor will smooth the current. So during the forward peak, the capacitor is charged up. So the forward peak here means the voltage is high. When the voltage is high, then the capacitor will charge up. That means it will store the energy in the capacitor. And then in between the forward peak, the capacitor will discharge. So in between of forward peak, the voltage is low. So the capacitor will discharge. Discharge here means will supply the energy. So maintain the potential difference across the resistor. So remember the resistor just now is the output. So number 4, a capacitor with greater capacitance will produce a smoother current. This is because the capacitor can store more charge. So this diagram shows half-wave rectification. That means half of the cycle the current can pass through, and then the second half no current pass through. That's why the graph here is 0. So when you add in a capacitor function is store the energy when the voltage is high, and then supply the energy when the voltage is getting lower. So where is the voltage is higher? So this area we can consider the voltage is higher. And then this area where the voltage is getting lower until 0. So this area we can say the voltage here is low. Then you can look at this diagram below. So this is where the capacitor is charging, because the voltage in this area is considered high. So voltage high supply to the resistor. So capacitor charging, store the energy. And then when the voltage is getting lower, voltage is decreasing, the capacitor is discharged. So that means in between this forward peak, so this one is what we call the forward peak, where the voltage is high. And then when the voltage is start to drop, then the capacitor will discharge. That means capacitor will supply the energy to the resistor. So you can see the current flowing is smoother now. because of the capacitor. Then you can see the graph here. This one is the capacitor supply the energy, and this is the energy from the source or from the battery. Not the battery, from the power supply, because we are using AC. So this is capacitor charging, and this is where the capacitor discharge. And this diagram is the full wave rectification. So same as the half wave rectification, capacitor charging at the forward peak. So this one is the forward peak, and this is the area where the voltage is low. So as long as the voltage is low, then the capacitor will start to supply the energy. Then finally, we look at some example which involve the question with the semiconductor diode. So the diagram shows the rectification circuit consists of diode and a resistor R. So the trace of the current flow in the resistor R shown in the CRO. Alright, so this one is the half wave rectification because only using one diode. So resistor here, this one is the output through the CRO. We can see the pattern of the half wave rectification current. So this is the DC current because current flow in one direction only. So what is meant by the rectification? So it is the process. It is a process of converting AC to DC current. So diagram B shows the combination of 4 diodes to connect to the AC power supply. So complete the diagram by drawing the 4 diodes in the bridge rectifier. So normally the question will ask you to draw the 4 diodes. So the direction is important, must be correct. So this is how you draw the diode for D1, D2, D3, D4. And then state the direction of the current flows when X is more positive than Y. X is more positive, that means the current flow from X to Y. So which diode you need to pass through when current flow from X to Y? So the current flow from X then to the D2, to the resistor, the output, and then go back from the D3 and then to Y. So this is the direction of the current flows. Then sketch the tracks of the rectified current. So it is a full wave rectification. And then C, name a component T that has to be connected to the circuit to smoothen the output voltage. So if we want to smooth the current, we need to add in capacitor. So explain how the component T is connected to the circuit and how the component T smoothen the rectified DC. So the component T, the capacitor, must be connected parallel with the resistor R. And then how the component smoothen the rectified DC. So the capacitor is charged. Then you need to explain capacitor is charging when the voltage is increasing or the forward peak just now. And then discharge when the output voltage is lower or decreasing. So you need to mention about charging and discharge or store the energy and supply the energy. So the discharge current from the capacitor will maintain a steady output voltage across the resistor. So that's all for the video. Thank you.